Hello and welcome back to BlueHat CyberSec Academy. This is the first lesson of Domain 4 of the Certified in Cybersecurity course. This domain is about network security concepts. It isn't just for exam preparation, it's also perfect for anyone interested in building a strong foundation in the world of cybersecurity. So, in this video, I am going to introduce networking basics, explain how networks operate, cover the OSI and TCP/IP models, and set the foundation for understanding communication protocols. Make sure to watch this video till the end, and if you haven't subscribed yet, hit that subscribe button and join BlueHat CyberSec Academy. Your path to becoming a cybersecurity professional starts right here. Now let's begin with the basics of networking. What is networking? A network is simply two or more computers linked together to share data, information, or resources. To properly establish secure data communications, it is important to explore all of the technologies involved in computer communications. From hardware and software to protocols and encryption and beyond, there are many details, standards, and procedures to be familiar with. Now let's move further and look at the types of networks. There are two basic types of networks. Local area network, or LAN. A local area network is a network typically spanning a single floor or building. This is commonly a limited geographical area. Wide area network, or WAN. A wide area network is the term usually assigned to the long-distance connections between geographically remote networks. Now let's move on to understanding some important network devices. Hubs are used to connect multiple devices in a network. They're less likely to be seen in business or corporate networks than in home networks. Hubs are wired devices and are not as smart as switches or routers. Rather than using a hub, you might consider using a switch, also known as an intelligent hub. Switches are wired devices that know the addresses of the devices connected to them and route traffic to that port or device rather than retransmitting to all devices, offering greater efficiency for traffic delivery and improving the overall throughput of data. Switches are smarter than hubs, but not as smart as routers. Switches can also create separate broadcast domains when used to create VLANs. Routers are used to control traffic flow on networks and are often used to connect similar networks and control traffic flow between them. Routers can be wired or wireless and can connect multiple switches. Smarter than hubs and switches, routers determine the most efficient route for the traffic to flow across the network. Great. Now let's move ahead and explore some more components used in networks. First of all, Ethernet, which is also known as IEEE 802.3, is a standard that defines wired connections of network devices. This standard, basically defines the way data is formatted over the wire to ensure disparate devices can communicate over the same cables. Now, let's talk about firewalls. Firewalls are essential tools in managing and controlling network traffic and protecting the network. A firewall is a network device used to filter traffic. It's typically deployed between a private network and the internet, but it can also be deployed between departments or segmented networks within an organization's overall network. Firewalls filter traffic based on a defined set of rules, also called filters, or an access control list. Moving on to servers. A server is a computer that provides information to other computers on a network. Some common servers are web servers, email servers, print servers, database servers, and file servers. All of these are, by design, networked and accessed in some way by a client computer. Servers are usually secured differently than workstations, just to protect the information they contain. And finally, endpoints. Endpoints are the ends of a network communication link. One end is often at a server where a resource resides, and the other end is often a client making a request to use a network resource. An endpoint can be another server, desktop workstation, laptop, tablet, mobile phone, or, any other end-user device. Now that these devices are clear, let's move on to how they are identified in a network. So, What is device addressing? Every network device is assigned a Media Access Control, or MAC, address. For example, a MAC address might look like 00-13-02-1F-58-F5. The first 3 bytes, or 24 bits, of the address denote the vendor or manufacturer of the physical network interface. No 2 devices can have the same MAC address in the same local network. Otherwise, an address conflict occurs. Now, regarding Internet Protocol, or IP, addresses. While MAC addresses are generally assigned in the firmware of the interface, IP hosts associate that address with a unique logical address. This logical IP address represents the network interface within the network and can be useful to maintain communications when a physical device is swapped with new hardware. Now let's move forward and take a quick look at networking through diagrams. So here's a quick overview. In a small business network, the lines depict wired connections. Notice how all devices behind the firewall connect via the network switch, and the firewall lies between the network switch and the internet. For a typical home network, the primary difference is that the router, firewall, and network switch are often combined into one device supplied by your internet provider, and that's shown here as the wireless access point. Now let's move on to networking models. There are, many different models, architectures, and standards out there that provide ways to interconnect different hardware and software systems with each other for the purposes of sharing information, coordinating their activities, and accomplishing joint or shared tasks. Computers and networks really emerge from the integration of communication devices, storage devices, processing devices, security devices, input devices, output devices, operating systems, software, services, data, and people. Translating the organization's security needs into safe, reliable, and effective network systems needs to start with a simple premise. The purpose of all communications is to exchange information and ideas between people and organizations so that they can get work done. Those simple goals can be re-expressed in network and security terms, such as provide reliable, managed communications between hosts and users, isolate functions in layers, use packets as the basis of communication, standardize routing, addressing, and control, allow layers beyond internet working to add functionality, and be vendor agnostic, scalable, and resilient. In the most basic form, a network model has at least 2 layers. The upper layer, also known as the host or application layer, is responsible for managing the integrity of a connection and controlling the session, as well as establishing, maintaining, and terminating communication sessions between 2 computers. It is also responsible for transforming data received from the application layer into a format that any system can understand. And finally, it allows applications to communicate and determines whether a remote communication partner is available and accessible. The lower layer is often referred to as the media or transport layer and is responsible for receiving bits from the physical connection medium and converting them into a frame. Frames are grouped into standardized sizes. So, think of frames as a bucket and the bits as water. If the buckets are sized similarly and the water is contained within the buckets, the data can be transported in a controlled manner. Route data is added to the frames of data to create packets. In other words, a destination address is added to the bucket. Once the buckets are ready to go, the host layer takes over. Now let's move on to the OSI model. The OSI model was developed to establish a common way to describe the communication structure for interconnected computer systems. The OSI model serves as an abstract framework, or, a theoretical model, for how protocols should function in an ideal world, on ideal hardware. So, the OSI model has become a common conceptual reference that is used to understand the communication of various hierarchical components, from software interfaces to physical hardware. The OSI model divides networking tasks into 7 distinct layers. Each layer is responsible for performing specific tasks or operations with the goal of supporting data exchange or network communication between two computers. The layers are interchangeably referenced by name or layer number. For example, Layer 3 is also known as the network layer. The layers are ordered specifically to indicate how information flows through the various levels of communication. Each layer communicates directly with the layer above and the layer below it. For example, Layer 3 communicates with both the data link, which is Layer 2, and transport, which is Layer 4. Layers. The application, presentation, and session layers, so that's layers 5 through 7, are commonly referred to simply as data. However, each layer has the potential to perform encapsulation. Encapsulation is the addition of header and possibly footer, or trailer, data by a protocol used at that layer of the OSI model. Encapsulation is particularly important when discussing transport, network, and data link layers, so layers 2 through 4, which all generally include some form of header. At the physical layer, or layer 1, the data unit is converted into binary, for example, 01010111, and sent across physical wires such as an Ethernet cable. It's worth mapping some common networking terminology to the OSI model so you can see the value in the conceptual model. When someone references an image file like a JPEG or PNG, we are talking about the presentation layer, which is layer 6. When discussing routers that are sending packets, we are discussing the network layer, or layer 3. When discussing switches, bridges, or WAPs sending frames, we are discussing the data link layer, or layer 2. When discussing logical ports such as NetBIOS, we are discussing the session layer, which is layer 5. And when discussing TCP or UDP, we are discussing the transport layer, or layer 4. So, encapsulation happens as the data moves down the OSI model, starting from the application layer all the way to the physical layer. As data gets encapsulated at each lower layer, the previous layer's header, payload, and footer are all treated as the next layer's payload. You'll notice that the data unit size actually increases as we move down the conceptual model, and the contents just keep getting encapsulated. Now, the reverse or inverse action takes place as data travels up the OSI model layers, from physical back to application. This is called de-encapsulation, or sometimes decapsulation. Here, the header and footer help interpret the data payload, and then they're discarded. As we move up the OSI model, the data unit becomes smaller. Now let's continue to the TCP/IP model. Transmission Control Protocol/Internet Protocol, or TCP/IP for short. The OSI model wasn't the first or only attempt to streamline networking protocols or establish a common communication standard. In fact, the most widely used protocol today, TCP/IP, was developed in the early 1970s. The OSI model was not developed until the late 1970s. The TCP/IP protocol stack focuses on the core functions of networking. Application layer defines the protocols for the transport layer. Transport layer permits data to move among devices. Internet layer creates and inserts packets. Network interface layer is about how data moves through the network. The most widely used protocol suite is TCP/IP, but it is not just a single protocol. Rather, it is a protocol stack comprising dozens of individual protocols. TCP/IP is a platform-independent protocol based on open standards. However, this is both a benefit and a drawback. TCP/IP can be found in just about every available operating system, but it consumes a significant amount of resources and is relatively easy to hack into because it was designed for ease of use rather than for security. At the application layer, TCP/IP protocols include Telnet File Transfer Protocol, which is FTP Simple Mail Transport Protocol, or SMTP, and Domain Name Service, which we call DNS. The two primary transport layer protocols of TCP/IP are TCP and UDP. TCP is a full duplex connection-oriented protocol, whereas UDP is a simplex connectionless protocol. In the Internet layer, Internet Control Message Protocol, or ICMP, is used to determine the health of a network or a specific link. ICMP is utilized by ping traceroute and other network management tools. The ping utility employs ICMP echo packets and bounces them off remote systems. So, you can use ping to determine whether the remote system is online, whether the remote system is responding promptly, whether the intermediary systems are supporting communications, and the level of performance efficiency at which the intermediary systems are communicating. That's it for this lesson. Thanks for watching. Don't stop here. Keep the learning going and check out the next video in the series. If you haven't already, make sure to like, share, and subscribe to BlueHat CyberSec Academy.